Okay, back again for the Common Core Geometry Regents Exam, August 2015. We'll finish up the part ones in this video. So let's see, where were we? Okay, number 13. All right, which single transformation was used to map triangle A onto triangle B? It's really looking like a rotation here. A line reflection, that's not going to get it done. Let's just maybe we label these points X, Y, Z. Okay, it looks to me like X ended up there. Y looks to be like that, and Z here. Okay. Translation, that would keep the slope of this side the same. It's not. You know, it preserves, translations preserve slope. That didn't happen here. Dilation, let's see. Dilations are tricky, but basically what we're going to do is we try to line up, we try to draw a line between corresponding points, and those are not going to converge. Maybe they are, but then that third one's not. All three of those lines should have converged for a dilation. Not going to happen. Line reflection, it does not look like I can find a single line of reflection, and I always check orientation for line reflections. What I mean by that is the arrangement of the letters. So X to Y to Z. If you go X to Y to Z, that is in a counterclockwise arrangement. X prime to Y prime to Z prime is in the same counterclockwise arrangement, so orientation's preserved. Cannot be a line reflection. Rotation was our first inclination, and we definitely proved that that's got to happen. Okay, number 14, let's see. All right, so this is a clockwise rotation, then a dilation. So we know the figures are similar just because of similarity transformations were performed. So we know that angle D is congruent to angle A by this similarity statement, basically, or at least the image. So let's see, E is going to be corresponding to B. All right, so let's take a look at these. Interesting choices here. Angles that are corresponding are not going to be in a ratio of 1 to 2. C and F are nope. So they're either going to be, you know, what we have to do is we have to find the corresponding angles, and if they have corresponding angles in a ratio, we're going to be able to use that. So let's see, A, is that corresponding to C? Okay, no. So A is not corresponding to F, so this one's probably not going to work. Let's check this one, make sure. B and E are corresponding, so that's going to be whatever it is. It doesn't matter what the angle measure is. This is going to be in a ratio of 1 to 1. These are going to be equal. Now, as long as C and F are corresponding, they are. So this is going to work, because C is equal to F, B is equal to E. We're going to get that one. Tricky problem. Number 15. A couple ways to do this one. Now, we've taught our students that opposite angles in this situation add to 180 when a quadrilateral is inscribed in a circle. Okay, and that's what we have here. So you could say this, you could teach your students this, opposite angles add to 180. Another way we could do this, instead of relying on that memory, you could say, okay, look at angle B. Angle B opens up to this arc AC. And that arc AC is 72 times 2, 144. Okay, so if you just focus on angle B, okay. Now what we have here is from A to C is a 144 degree angle. So 360 minus 144 is 216. So from here to here is 216, and angle D opens up to that. An inscribed angle that opens up to that arc. So it's going to be half. This angle is going to be half of that arc that it opens up to. So 216 divided by 2, 108, and you did see that this ended up working out, but there was another way to go about it. So this angle right here, 108. All right, let's create some space here. Let's get a little work space. All right, hemispherical tank. Hemisphere, so half sphere is what that means. And diameter equals 10 feet. Pounds per cubic foot, so the units of measure agree. That gives us a density right there. What's great about science, they pay attention carefully to the units of measure. If we utilize that strategy, it'll help us. It'll basically tell us what to do. So it'll show you how to do that too. Now, a hemisphere is a half sphere. Basically, you got a basketball or something like that cut in half. So what we would do is we would get the volume of the whole sphere. Let's say volume of a whole sphere. The formula comes right off of the formula sheet, 4/3 pi r cubed. If diameter is 10, remember the radius is going to be 5. Okay. And just keep in mind that we are calculating for a full sphere. We'll eventually have to cut that in half. Okay, when I do that, let's see. I get 523. Whoops, 59. And what we'll do is we'll take half of that. So for the hemisphere, your volume is going to be half of that. And that turns out to being 261.799. Okay, so that's the volume or the space. Now density is stuff over. So density, what I like to teach my students is density is stuff over space. Okay, so the stuff is the weight of the water. Okay, and the space is the volume. All right. Now, in this problem, though, they give us the density. So I like to use the units of measure to my advantage. They give us 62.4 pounds for every 1 cubic foot, and that's what that means. Now, science does this, and we can utilize that strategy. Okay. So what we have here is a volume which is feet cubed. It tells us, if we use a proportion, it tells us right where to put that. So we're going to put the 261.799. It's really feet cubed. And then we'll get X pounds. And now we get to use this to our advantage when we cross multiply. Now you won't see me carry on the units. It was just helping me set it up. So X is going to be whatever 62.4 times 261.799 is. And it looks like it's 16,336.3, and that's going to be the weight of the water. That's going to be pounds. All right. Similarity, okay. All right, it looks like, all right, they're telling us the triangles are similar. So you've got this triangle similar to that one. And what we would go through, unfortunately, is we've got to test it out. Okay, it looks like all of them start out with AD to be AB. All right, if we do that, AD to AB, you know, we're looking at the similarity statement up there, and it's going to help us set up the first fraction. And all of these are AC to AC, AE to AC. Yeah, so we're going to put that on top. And there we go. So now what we're going to do is we're just going to test all the proportions, and we're going to see which one's cross products are equal. So here we go. 3 is to 6 is 4 is to 12 is a question mark. when you cross multiply, you get 36. Okay, we can see that one's not going to work. 36 is not equal to 24, so we get rid of it. All right, this is just going to take a little bit of a grind. There's probably a better way, but this is the way I chose, and so here we go. 5 is to 8. That one's not going to work. I can tell that right now. I probably would not go through the process if I wasn't making this video. You know, I'd skip right over that one. I'd know it wasn't going to work. Okay, so get rid of that one. Whoops, crossed off the wrong one. All right, so we got rid of choice 2. Now we're trying choice 3 right now. 3 to 9, 5 to 10. Not going to work. So that's not going to work either. We're down to the last one. This one hopefully will. Yes, it does. I can see it now. 2 times 15 does equal 6 times 5. All right, that's the one. Of course, there were probably more efficient ways of doing that, but that's the way I decided to do it. All right, number 18. Oops, went too far. All right, inscribed. Triangle is inscribed in a circle. Oh, circle O. Here's what this identifies right there. It identifies that that's the center. We name circles by their center. So that tells us FG is a diameter because it passes through the center. That's important to know. And FH is the same as OG. Okay, so basically you're looking at this. Radii of the same circle are all the same. So if that's 6, then so's that, so's that. Now these two are congruent, so that is also 6. What we have in here to focus on, F, H, and O, they're all 6s. Okay, so this is an equilateral triangle. That angle is 60 degrees. Now they want the sector formed by FOH, so this here. Okay, they want to know what's the area of that. Okay, so we want area of this stuff in here. All right, what I like to do with this problem is first get the area of the full circle. I think that's the way that works for me the best, anyway. So full circle, pi r squared, and the radius is 6, so in terms of pi, it's 36 pi. Now I kind of peeked at the choices. I don't see any decimal answers. I see all answers, what we call in terms of pi. So I simply left it that way. All right, now this is the full circle. What we want to look at is a full circle is 360 degrees. 60 degrees out of 360 degrees is basically, if you do the math, whoops, it's 1/6. So if I want to know the area of that sector, it's 1/6 of the area of the full circle. And that's probably your best bet right there. Okay, so area of the sector is going to be 6 pi. There's a lot of ways to do that problem. I just decided to go that way. So 19, okay. So they're telling us again that this is a similar figure situation. Basically, what we're going to look at is we're going to take this similarity statement. Okay, they give us that. Might help. We're going to look at this similarity statement, and we're going to start deciding which of the proportions is going to work. So we've got to make sure the corresponding sides are either one above the other, or, you know, it's across from each other that way. Okay. So what we're going to look at first is, if you look at CE, third and second letter, that's good. Those are corresponding up and down. Now, what also needs to happen is a side from this triangle has to be on top, but it's not. It went over here. That's going to be wrong. Okay. AE to BE. Okay. AC to BD. That's going to work. if you look, this is nice right here. AE is the first and second letter, BE as well. AC is on the first triangle, all right? And BD is its corresponding. That's going to work. The rest of them are probably not going to work. Let's check it out. Okay, EC and AE are on the same triangle. So if EC's corresponding better be BE. It's not. It's ED. So that's not going to work. And I'm sure this one's going to fail as well somehow. ED's over here. That's matching. But AC is back over here on this triangle, so they're not going to work. All right, that's how you go through this. Again, it's just a grinded out problem, and that's what we found. All right, a triangle is dilated by a scale factor of 3 with a center of dilation at the origin. Which statement is true? Okay. Let's jump to this one. The slope. Remember, dilations preserve slope, so we cannot triple the slope. That's definitely not going to work. Dilations preserve slope. Okay, so does a translation. So you got to make sure you understand those concepts. Measure of each angle? No. When you dilate, you're going to get corresponding angles congruent. So that's no good. All right. Now, all right, what they're looking to teach you here is the ratio of the sides. The sides ratio is equal to the perimeter ratio because it's all one-dimensional measurements. When you have one-dimensional measurements like length, okay, there's a length, no width, those ratios are going to be the same. When you go to 2 dimensions, which is area, that's length and width. So you're basically going to multiply the ratio together. Okay. Now, if you have a triangle that's dilated by a scale factor of 3, okay, what's going to happen is the ratio of the sides is going to be 1 to 3. Now, the ratio of the areas, though, is going to be 2-dimensional. You're going to square those. 1 squared to 3 squared is the same as 1 to 9. So that's where this 9 times, no, that's perimeter. Whoops. So perimeter 9 times, no, because it's going to have the same ratio. They're one-dimensional values. The area is 9 times the area. That is going to work. If you wanted to extend this problem and teach students some more, volume is 3-dimensional. And what would happen is we'd take this and we'd cube it. It'd be 1 to 27. So if somehow we had a 3D shape, that's what would happen. So if you had volumes of cubes involved, maybe. All right. Let's see. Regular pyramid. Let's create some space here to work. Regular pyramid. So what we have to do with a square base. Okay. Before I jump to conclusions, yeah, it's volume. Okay. So pyramid, it's 1/3 area of the base times the height of the pyramid. Okay. These are tricky. So this B is the area of the entire base. Okay, so what we have is square base. Oh, all right. So what we're going to do is we're going to replace the things we know. We know the volume. So volume is given to us here. 2592276 and 146.5. Okay. So I'm going to combine like terms. Let's see, what were let's see, 21. Okay, so I just rewrote this. And I got 48.83 times B. It's a decimal that keeps going, but I'm going to go like that. All right, so I multiplied those together to start off. Now we're going to divide both sides by whatever that is. And we're going to come up with 53084.2. Now, that's the area of the base. Now, since it's a square, what we have is basically x times x equals 53,084, right? So we're going to now square root both sides to get about 230.4. And there we go. Choice 4. Not bad. All right. So quick, we'd have to graph this one. -3, 1. Let's call this, let's label it A, B, C, D. So it's going to be A, 0, 3, 5, 2, and -1, -2. Okay. You can get a guess to start out with out of these. Probably not. Definitely not. Probably not. Okay, so I'm going to look for evidence that it's a trapezoid to make sure. 1, 2, 3. It's 3 across, 2 up and down. So the slope of AB, the rise is 2, the run is 3, and it's a positive slope. Let's check out CD. Got to be careful here how we graphed it. Okay, I get 4 and 6. Let's see, the run is 6, the rise is 4, and it's positive. Yeah, same slope. So it has a pair of opposite sides parallel. That's not gonna, you're not gonna get anything out of that. You're not gonna get, this might be a right angle, but this is definitely not. So we're gonna be looking at a trapezoid. Pretty safe to say. If you want to prove it, you can continue and make sure. But that's good enough for part 1. All right. Dilation. What's the pre-image? Okay, so it got smaller. All right, so the scale factor is less than 1. Between 0 and 1, I should say. Usually we use scale factor of k. So it's between 0 and 1 because it got smaller. All right? But it's still on the same side of the center, so it's a positive scale factor. Okay, so our ratio has to be something that is between 0 and 1. These are out. Okay, here's how I would probably do this. I like to write down pre-image times scale factor equals image. And my pre-image is ACD. So let's go with just the up and down. That's easiest, in my opinion. 2, 3, 4, 5, 6. So that's 6. That's the pre-image. K is an unknown scale factor. I don't know why we use K. We just do. And from there's 4. We're going to divide by 6, and we get K is 4/6. Same as 2/3. There it is. And last one for this batch. Okay. Dilation scale factor of 2. Okay. I like to graph. Oops. Yeah, that's right. Start at -1, up 3/1. Okay, that's the original line. If we dilate by a scale factor of 2, we know we're going to get a parallel line. We know that. Well, that's not a question because that's all our choices. Now this, oh, wait a minute. We did not dilate based on the center at the origin. The center is 3, 8. We're still going to get a parallel line. All right, this is not going to be easy. 2, 3. Oh, right there. There is our center of dilation. Okay, here's the interesting part there. When we dilate a line and the center of dilation is on the line, we get the same exact line. So that's going to be our equation. We don't have to really do anything. In other cases, let's say the center was not on the line, we'd have to, double the distance from the center. But the distance from the center is 0, so we just keep the same line. All right, so that's this one. center of dilation on the line. So same exact line. That's important to remember. Thanks for tuning in. Hopefully this is helpful.